Gravity is not what you think it is. We feel it every moment of our lives. It's the invisible force that pulls an apple from a branch to the ground. It's the cosmic glue that holds our Earth in orbit around the sun. Our sun in its place within the Milky Way galaxy. We live and breathe by its rules. Yet this familiar force holds one of the deepest mysteries in science. At the tiniest scales, the world of quantum physics, gravity doesn't play by the same rules. This is the Great Showdown, the fundamental conflict at the heart of modern physics. We currently have two spectacular theories. First, Albert Einstein's general relativity, rule book for the big stuff, planets, stars, galaxies, the large-scale structure of the cosmos. Einstein reimagined gravity, space-time as a shaped fabric. Massive objects like the sun warp space-time, creating curves. Smaller objects, like Earth, follow those curves. It's elegant and explains GPS and gravitational lensing. Second, quantum mechanics, physics of the very, very small, atoms, electrons, fundamental particles. For decades, the search for quantum gravity has been dominated by two major contenders, like two heavyweight champions in a long-running title fight. The first, and perhaps the more famous of the two, is string theory. This idea starts with a bold and simple premise. What if the most fundamental building blocks of reality aren't point-like particles, but tiny, vibrating, one-dimensional loops of energy called strings? It's a profound shift in perspective. If you could zoom in on an electron, you wouldn't see a dot. You'd see a little string wiggling and vibrating in a specific way. It's a cosmic symphony where everything is made of music. The different ways a string can vibrate correspond to all the different particles we see in nature. One vibration mode might look like an electron, another might look like a photon, and so on. Crucially, one particular mode of vibration has the exact properties of the graviton, the hypothetical quantum particle of gravity. In this way, gravity isn't added into the theory, it emerges naturally from the vibrations of the strings themselves. The theory is mathematically beautiful, but it comes with a catch. It requires the universe to have more dimensions than the 3 of space and 1 of time that we experience, perhaps as many as 10 or 11 in total. This theory takes a more conservative approach, starting directly from Einstein's ideas about space-time. Instead of adding extra dimensions or new kinds of stuff like strings, LQG asks a different question. What if space-time itself is quantized? This means that space isn't a smooth, continuous sheet. If you could zoom into an unbelievably small scale, the Planck scale, you would find that space is made of indivisible, discrete chunks or atoms of space-time. These fundamental grains are woven together into a network of connections, like a quantum fabric. In the world of loop quantum gravity, area and volume themselves come in minimum sizes. You can't have a piece of space smaller than a certain amount, just as you can't have less than 1 quantum of light. This pixelated structure of space-time elegantly resolves the infinities that plague other approaches to quantum gravity. Black hole singularities, for instance, wouldn't be infinitely dense points, but regions of incredibly dense but finite quantum geometry. LQG offers a compelling picture of a granular cosmos, but like string theory, it operates at energy scales that are fantastically beyond our current ability to test directly in a laboratory. In recent years, the landscape of quantum gravity research has become much more diverse, with a wave of creative and sometimes startling new ideas. Many of these proposals challenge a core assumption string theory, loop quantum gravity. They suggest that gravity might not be a fundamental force of nature at all. Instead, it could be an emergent phenomenon, arising from the collective behavior of microscopic components, much like the temperature of a gas emerges from the motion of individual atoms. You can't talk about the temperature of a single atom, only the group. One of the most intriguing of these emergent ideas is called entropic gravity. This theory links gravity to the laws of thermodynamics, specifically to entropy. Entropy is a measure of disorder, or more precisely, the amount of information hidden within a physical system. The idea is that gravity isn't a fundamental pull, but an entropic force, a statistical tendency for things to happen. It suggests that space-time and gravity emerge from how information is arranged in the universe. In this view, gravity is the universe's way of maximizing disorder, like how coffee and milk eventually mix into a uniform solution. This connection between gravity thermodynamics information has sparked a whole field of inquiry. Some researchers are exploring how gravity might arise from quantum information theory. One proposal says the geometry of spacetime is directly related to entanglement between quantum particles. The more entangled two regions are, the closer they are geometrically. Another idea, based on quantum relative entropy, proposes that changes in quantum information flow create spacetime curvature, what we call gravity. These ideas are abstract, but point to a deep link between the stuff of reality and the bits of information that describe it. Taking this further, some theories propose gravity could emerge from electromagnetism. This is a very bold claim. It suggests that at the quantum level, interactions between charged particles' photons might conspire to produce the long-range attractive force we call gravity. Others propose a new field, the G field, connected to the fundamental constants of nature. This field could provide a mechanism for gravity to emerge, and might explain other mysteries like dark matter. While many physicists are trying to quantize gravity, a few brave souls are exploring an even more radical possibility. What if we've been trying to solve the problem backward? The standard approach assumes that quantum mechanics is fundamental, and that it's Einstein's theory of gravity that needs to be modified to fit the quantum world. But what if it's the other way around? This line of thinking, sometimes called post-quantum classical gravity, suggests space-time remains fundamentally classical, just as Einstein described it. It's not pixelated or made of strings. Instead, quantum theory itself needs to be changed. Quantum mechanics has been unshakably successful for over a century. However, these new models say, when gravitational fields become extremely strong, quantum rules start to break down. For instance, a fundamental level of randomness or information loss in nature where the perfect predictability of quantum evolution is disrupted by interaction with classical space-time. This avoids the need to find a graviton or quantize space-time, but it demands rewriting the foundations of quantum physics. It's a long shot, but it forces us to question basic assumptions. Another promising direction tries to describe gravity in the same language as the other forces. So we have all these fascinating and clever ideas, strings loops, emergent gravity, and more. Why don't we just do an experiment and see which one is right? The answer is incredibly frustrating. The effects of quantum gravity are astronomically small and only become significant at an energy scale so high it's almost unimaginable. This is known as the Planck scale. To probe this scale directly, we would need a particle accelerator the size of our entire galaxy. That's a bit beyond our current engineering capabilities, to say the least. This immense gap between theory and experiment is the biggest roadblock in the quest for quantum gravity. The problem is that gravity is ridiculously weak compared to the other forces. Think about it. A tiny refrigerator magnet can lift a paperclip, defeating the gravitational pull of the entire planet Earth. This weakness means that the quantum graininess of gravity, if it exists, is hidden from us at all but the most extreme energies. In our everyday world, and even in our most powerful particle colliders like the Large Hadron Collider, space-time appears perfectly smooth and classical. We are like people trying to figure out if a photograph is made of pixels by looking at it from a mile away. The detail is just too fine to see. This experimental wall has led some critics to worry that the field has become disconnected from empirical science, drifting into the realm of pure mathematical speculation. They haven't given up on finding cracks in the experimental wall. Instead of brute force, they're designing incredibly subtle, clever experiments. These experiments listen for the faint whispers of quantum gravity in our low-energy world. They don't probe the Planck scale directly, but they test core principles any quantum gravity theory must obey. It's like listening for the echo of a distant explosion. One exciting avenue: tabletop experiments, tiny quantum-controlled masses on a lab bench. Take a microscopic object, cool it until it behaves as a single quantum entity. Carefully measure how it interacts with gravity. Can a quantum mass be in a superposition of two locations at once? If so, what does its gravitational field look like? These tests ask, is gravity itself a quantum phenomenon? If yes, it would be revolutionary. Another idea, gravitationally mediated entanglement. Place two quantum particles near each other, prevent any interaction except gravity. If they become quantum entangled, their fates linked, it would indicate gravity carries quantum information. Observing this is extraordinarily difficult, but research groups worldwide are developing the technology. A successful test would be a landmark. Finally, turn telescopes to the sky. Use the cosmos as a lab. The early universe was extremely energetic and dense, where quantum gravity dominated. Those effects may have left faint imprints on the cosmic microwave background. or in the way galaxies are distributed across the universe. Extreme mergers, black holes and neutron stars, create powerful gravitational waves. Studying these signals with increasing precision might reveal tiny anomalies that don't fit Einstein, pointing toward a new, more complete picture of gravity. We need a theory of quantum gravity. That's the big goal. The showdown between gravity and the quantum world remains the biggest unsolved problem in fundamental physics. We stand at a fascinating crossroads, with a landscape of competing ideas. The old champions, string theory, loop quantum gravity, still offer profound and deeply explored pathways. But they are now joined by a host of nimble challengers who suggest gravity might be an illusion, an emergent effect of information thermodynamics or other forces. Still others are rewriting the rulebooks of quantum mechanics or recasting gravity in a more familiar language. The field is more vibrant, more diverse, and more full of creative tension than ever before. We are, in a very real sense, explorers mapping an unknown continent with only a few tantalizing clues to guide us. The final answer is not yet in sight. We don't know if space-time is a smooth sheet, a pixelated grid, a hologram projected from a distant boundary, or something else entirely that we haven't even imagined yet. Each possibility would fundamentally alter our conception of reality. The search for quantum gravity is not just about finding a new equation, it is a quest to understand what space, time, and matter truly are at their deepest level. It's a journey to the very bottom of the rabbit hole. What is so inspiring about this quest is that even in the absence of a final answer, the pursuit itself pushes the boundaries of human knowledge. It drives innovations in mathematics, cosmology, and experimental physics. The clever new tests being proposed, whether on a tabletop or through a telescope, stretch our technological capabilities to their absolute limits. The theoretical ideas, even the ones that turn out to be wrong, force us to think more deeply and creatively about the nature of the universe. This is the engine of scientific progress, asking the biggest questions even when the answers seem impossibly out of reach. The story of quantum gravity is an unwritten chapter in the book of science, and we are living through the process of its creation. We should remain hopeful, but also honest about the scale of the challenge. The final theory might come from an established framework, a radical new idea, or a surprise observation that no one predicted. But one thing is certain: the universe has a secret to tell us about how its largest structures and its smallest components are woven together. The quest to hear that secret is one of the grandest adventures in the history of human thought. So I encourage you to learn more, to stay curious, and to keep looking up. The cosmos is waiting. Time to music-only beat. Ajin December Comberdan Sound. Huge thanks to Thunderbird Perch for making this video possible. Please subscribe, like, and share. Think about it, a new world awaits.